Hey everyone, and welcome back to the Explainer. Today we're diving into a really incredible research paper. It's called TriSplat, Simulation-Ready Feed-Forward 3D Scene Reconstruction. This work comes to us from Weizhi Wang and a team of 7 other brilliant researchers, and honestly, it's a massive breakthrough. It is literally a game changer for the tech and gaming industries. If you've been tracking the insanely fast progress in AI-generated graphics lately, you're definitely going to want to pay close attention here, because we're looking at a fundamental shift in how digital environments are actually built.
Just think about it. What if AI could generate playable 3D worlds instantly? We aren't just talking about pretty pictures or cinematic fly-throughs, you know. We're talking about actual solid worlds you can interact with right off the bat. Okay, let's dive into this, because to really grasp why this question is so crucial, we first need to look at the massive bottleneck that's been holding back 3D generation up until now. Section 1. The 3D scene bottleneck. So here's the deal. While current AI-generated 3D scenes might look absolutely stunning to the human eye, there's a hidden, fundamental problem lurking just beneath the surface. Right now, most of our sparse-view 3D reconstruction methods rely on something called Gaussian primitives. You can basically think of these as fuzzy clouds of color. They only imply a surface. They don't actually create one. Sure, they look fantastic, but they aren't solid. Now contrast that with our actual goal here, oriented triangles. Triangles form a solid, simulation-ready mesh. It's like imagine trying to drop a bouncing ball into a scene made purely of those Gaussian primitives. What happens? It wouldn't bounce. No way. It would just fall right through because there's literally no solid surface for it to hit, just fuzzy, colored clouds. For any kind of real physics reasoning or, say, embodied AI interaction, Gaussians alone just don't cut it.
And because those Gaussian clouds aren't actually solid, if you want to extract a usable mesh from them for simulations, you're stuck doing these really messy, incredibly expensive post-hoc cleanup steps. You basically have to go in and fix the data after the fact. And honestly, that completely breaks the whole promise of having a fast, feed-forward AI pipeline. This bottleneck becomes super pronounced in what researchers call pose-free settings. That's when the AI basically has to guess both the camera parameters and the entire scene structure at the exact same time, using just a handful of sparse, completely unorganized images. It's heavily computational and just wildly inefficient.
All right, Section 2, Introducing TriSplat.
So to understand how this TriSplat system completely flips the script on 3D generation, let's quickly demystify some of the jargon here. What exactly is feed-forward reconstruction? Well, essentially, it's a network process that predicts explicit 3D scene primitives directly from input images in one single direct pass. Basically, in plain English, feed-forward means it happens instantly. You don't need that messy, super expensive cleanup step we just talked about. It goes straight from 2D images to 3D primitives in one fell swoop.
Now, what's really interesting about this slide is that during this single pass, TriSplat completely ditches those fluffy Gaussian clouds. Instead, it natively exports exactly what we need: simulation-ready mesh scenes that are built right out of solid-oriented triangle primitives. It also spits out local 3D point maps, camera poses, and even optional intrinsics. By representing the entire scene with actual solid triangles from the very beginning, we completely bypass the need to convert anything later on. It is ready to go.
Section 3. Under the hood.
Okay, let's look at exactly how the TriSplat architecture pulls off this incredible feat. First, the pipeline takes in those sparse-view images. Then, step 2, it predicts local 3D point maps. But step 3 is where the magic actually happens. Instead of just wildly guessing how these triangles should be oriented, which, the paper refers to as treating it as an unconstrained latent variable, TriSplat refuses to do that. It methodically constructs geometry normals directly from those predicted point maps and then refines them using an image-conditioned normal head. Finally, step 4, it converts these into stable local frames so it can parameterize the triangles. It's building the structure deliberately, step by step, rather than just throwing darts in the dark and hoping for the best.
And to make sure the system actually learns all this properly, the researchers threw in a really clever engineering trick called a mononormal bootstrap schedule. See, when the AI first starts training, it's pretty prone to getting confused, right? This bootstrap schedule steps in and stabilizes the system during those absolutely crucial early phases of training. It essentially guarantees that the foundation of the 3D mesh is being built on solid, reliable math right from the jump.
The second half of their training strategy relies on what they call opacity and blur scheduling, and this brilliantly illustrates how the system progressively sharpens its learned surface representation over time. Think of it kind of like a digital sculptor, taking a really rough block of clay and slowly, meticulously carving it down into a sharp, usable mesh. The system just keeps fine-tuning itself until the final output is totally crisp and ready for direct extraction.
Moving right along to Section 4, real-world testing. Now, the researchers didn't just drop a theoretical pipeline and walk away. They actually put this to the test on some major heavy-hitting data sets like RealEstate10K and DL3DV. And the results? When stacked up against those older Gaussian baselines, TriSplat produces incredibly geometry-faithful reconstructions. Where the old methods leave you stuck with indirect, fuzzy surfaces that need expensive post-hoc cleanup, TriSplat hands you true physical structure. And the best part? It does all this while keeping the novel view rendering quality highly competitive. So it absolutely beats the baselines on physical structure, and it doesn't even sacrifice the visuals to do it.
Which brings us to Section 5, simulation-ready futures. All right, so what does all of this actually mean for software devs, 3D artists, or gamers? Well, I'm going to read straight from the paper's abstract here. Quote, the output can be directly ingested by physics engines, collision detectors, and standard rendering pipelines without any conversion. End quote. So the crucial point is that because the rendering primitives are literal surface triangles, TriSplat is a true plug-and-play solution. You feed your 2D images in, and you get a solid, physics-ready, interactive 3D environment out. No messy conversions, no waiting around. Just boom, done.
So I'll leave you with this. How will instant, physics-ready environments change the way we interact with digital media? Seriously, just imagine a future where literally any photo or video you take can instantly become a playable, solid digital reality. TriSplat is actively unlocking exactly that future, making feed-forward 3D scene reconstruction an actual practical reality today. Thanks so much for joining me for this explainer, and I really hope this sparked your curiosity to go check out the absolute cutting edge of AI generation.